Welcome to the mass transfer subject shooting for gate lecture 3. Today we are going to look ahead the general molecular transport equation which says the rate of a transfer process is equivalent to some driving force divided by resistance. In general, we call this as an equation which states that a driving force is needed to overcome resistance in order to transport a property. That means, transport a property from one place to another place, or one substance to another substance, one phase to another phase, like that. Imagine or correlating with what you call the Ohm's law. Ohm's law says current, the rate of flow of electricity is proportional to voltage, is inversely proportional to the resistance. If I write this as equation, I is equal to V by R. Actually, this is a Ohm's law, right? So we generally write as V is equal to IR, but this is the resistance and this is the driving force. So then there is a current flow. So if we correlate this particular operation to a transport processes, we can write rate of a transfer process is equal to driving force by resistance. Now, the equation, molecular transport or diffusion of a property is written as psi z is equal to minus delta d tau or dz. So what is this? This represents flux of a property as amount of property being transferred per unit time per unit area. This is known as what? Flux. Flux is amount of property. Okay, let me write it here. This is nothing but amount of property transferred per second per unit cross-sectional area. But what is that particular cross-sectional area which is perpendicular to the direction, perpendicular to z direction? So this is z direction. So in the perpendicular direction, we need to actually address this. So you remember the left-hand side, this term is a flux. Now the right-hand side, the terms what we see, this term, we writing as is a proportionality constant. Don't confuse with rho or something, delta or something like that. It is called as diffusivity. Diffusivity, the units being meter square per second. And the third quantity, this particular, symbol, tau, is the concentration of a property. Concentration of the property in the amount of property per volume. So you can see this, this is the concentration of the property in the amount of property per meter cube. Z is the distance in the direction of the flow. So what is the Z1? What is the next term? Next term available with us? That is Z. Z is the distance in the direction of the flow, that is in meters. Hope this is clear to all of you here at this place. So we started with a general molecular transport equation in this particular session. Now let us see the equations with respect to three transport processes or three transfer processes. First one is momentum. See, whenever I write a pump symbol, I am saying it is a momentum transfer or momentum transport because we are transferring a fluid from one place to another place. In this, the equation would be tau zx is equal to minus mu by rho d of vx rho by dz. Very simple. Okay. So this is again flux, but this year we denote this as a momentum transferred per second per meter square. So this is momentum transferred per second per meter square. And then we have mu by rho. So then is another term called, this is one term, another term called mu by rho. Mu by rho is the kinematic viscosity. Mu by rho is known as kinematic viscosity. Mu by rho is known as kinematic viscosity. Kinematic viscosity. That is given by meter square per second. Z is the distance in meters, whereas V, X, and rho, this is the momentum per meter cube. So what is the units of momentum we have? So if you see the momentum units as it is, we have kg meter per second. That is mass into velocity. See, at this point of time, I'm detailing each and everything because this will help not only in mass transfer as well as in another transport processes also. Okay, let me rub this off. Oh, sorry. Yeah, let us retain this. Now, the another one, now you can see. Yeah, the next one is, we go to heat transfer. Okay, or thermal energy transfer, heat transfer or thermal energy transfer. In this, the equation would be written in terms of qz by a, that is left hand side is qz by a is equal to minus alpha d of rho cpt by dz. It is, remember, this is always the small z is, it is z is distance, that is in small letter only. So the left hand side is the heat flux, total is known as heat flux because it is per unit area. That is, this is here, the units here is watt per meter square. Alpha is the thermal diffusivity. Whereas in the molecular diffusion, that means with respect to the momentum transfer, molecular diffusion, we are referring to heat transfer now. Molecular diffusion with respect to momentum transfer, it is mu by rho, that is kinetic viscosity. Now what we are seeing, the another term known as thermal diffusivity. Again, the units are meter square per second. Here again, the terms, this term total rho CPT is joule per meter cube. See, as similar as this Vx rho. Vx rho is again momentum per meter cube. Okay, it is again what? Momentum per meter cube. Here we have rho Cp joule per meter cube. That is what you have to remember. Okay, let's come to our mass transfer now. Let's come to our mass transfer. Molecular diffusion of mass. What we are referring as the molecular diffusion of mass. See, okay, molecular diffusion of mass. So the equation which is written as is JAZ. See, whenever we write molecular, we write it as capital J minus DAB dCA by dZ. Here again, this is concentration units. Concentration units is gram mole A per meter. If I write gram mole, it is centimeter cube. If I write, SI units, this kg mole per meter cube. Kg per meter cube. The next one, what is the next one? The left hand side, what we have? Ja, it is known as molar flux of component A in the Z direction. In the Z direction, due to molecular diffusion. The units again were what? Kg mole of A per time per meter square. Here the term is DAB. DAB is known as molecular diffusivity. Hope the terms are clear, right? Molecular diffusivity, again, when there is a mass transfer molecular diffusion, we say from A in B. Molecular diffusivity of the molecule A in B. Again, the units are meter square per second. So in conclusion, we have general equation written phi z is equal to minus something, or this is a general equation of transport. We have written equation of transport. Equation of transport for what? First of all, we have written equation of transport for tau zx. We have written equation for tau zx. That will become minus mu by rho into something. We have written equation called, what is the next equation if you remember? That is heat transfer. We have written heat flux, that is Qz by A is equal to minus alpha into again a term. In the mass transfer, we have written equation called JAZ star is equal to minus DAV into again the term, the gradient, or as per the distance. So in the bottom, wherever we write dz, dz, dz. This particular term, it tells us our concern. If you write dCA, it is mass transfer. If you write dt, that means temperature gradient, not just T here, because we need to refer the into rho Cp. Yeah, so let us see that rho Cpt, and here you write momentum into, or rather, it's a momentum per units, right? So this is Vx into rho. I think I'm making some sense, right? Which is nothing but momentum per meter cube. So it is momentum per meter cube. So here the terms which are very important are to understand are what? They are this similarity, this one, and this one. Okay. So this is a general, what you call, discussion on the molecular transport equation in three different processes. What is the first one? First one is psi z is equal to minus delta d tau by dz. The left hand side is defined as flux of the property as amount of property being transferred per unit time per cross sectional area. Whereas a tau, this tau, what we said, is the concentration of the property in the amount of property per meter cube. This delta, what we are writing delta is a proportionality constant called diffusivity. It is known as kinematic viscosity, thermal diffusivity, and molecular diffusivity. Z is the distance in the direction of the flow. Okay. So we came to an end of the lecture 3. Yeah. So it has become a little lengthier, but it is required. We'll meet in lecture 4.